Good morning students. Today we'll be discussing about the properties of continuous time Fourier transform. Various type of properties are listed out here, and the purpose of going for all these continuous time Fourier transform is to reduce the complexity in the integration that has to be done when doing Fourier transform using the conventional method. So in conventional method, when a signal is given, you will try to find the Fourier transform by applying the formula. When you do that, you will be coming across a lot of complex steps, right? Integration steps. So if you want to avoid that, then we can make use of the properties. So here we have mentioned a few of the properties which are very important. So first one, linearity, property of continuous Fourier transform. We will go like this. First, the statement of the property will be given, and then consequently the proof will be discussed. So here the notation of how the statement is given is important. So here the meaning is x1 of t is the time domain signal, x1 of j omega is the Fourier transform signal obtained by performing Ctft. So we can tell that x1 of j omega is the Fourier transform of x1 of t, right? x2 of t, continuous time Fourier transform, is x2 of j omega. If this is the case, then ax1 of t plus bx2 of t Ctft will be equal to ax1 of j omega plus bx2 of j omega, right? That is, in time domain, if the signals are scaled and added together, the property goes like this. How do you explain this property? You can tell that if two signals are scaled in time domain and added together, then they will also be scaled in frequency domain and added together. So you can see that the individual transforms in frequency domain are scaled and then added together. So proof for this, for starting with the proof of this, we have to go for the formula for Ctft. So we know this is a formula for Ctft. X of j omega equal to integration t equal to minus infinity to infinity x of t e power minus j omega t dt. So it should be written as dt is missing over here. So you have to write it as dt, right? So hence now we can have to split it into two individual signals. So Fourier transform of the first signal x1 of j omega can be given as integration minus infinity to infinity x1 of t e power minus j omega t dt. Now multiply the entire equation by a. So what we get? A into x1 of j omega is equal to the same thing. Just we are multiplying this entire equation by a. This is equation number 1, right? So next, similarly you have to do it for the second signal. So again second signal x2 of j omega will be equal to integration and then multiply it together by means of b, right? So that will give rise to equation number 2. So now add equation 1 and 2. So when you add equation 1 and 2, that is previous equation 1 and 2, you will be getting on the left hand side ax1 of j omega plus bx2 of j omega. So this is b x2 of j omega on the left hand side, and then correspondingly here you will be getting ax1 of t plus bx2 of t, and this will be equation number 3, right? So now in this, which are all the terms that are common? You can see that this integration is common, and then e power minus j omega t dt is common. So take out those common integration. So remaining will be ax1 plus bx2 e power minus j omega t. Right? Now you compare this equation 4, right, with your conventional equation that is given here, right? What is a conventional equation for Fourier transform? We have seen over here. What is Fourier transform equation? Fourier transform equation is this, right? So if you have here x of t e integral minus infinity to infinity e power minus j omega t dt, then the corresponding Fourier transform is x of j omega. So when you compare this with this equation, we can very well infer that, right? What we can infer is, if you compare with that normal equation, the left hand side represents the continuous time Fourier transform of the signal ax1 of t plus bx2 of t. See, the remaining terms are same, integration minus infinity to infinity and e power minus j omega t dt. So we can tell that Ax1 of j omega plus Bx2 of j omega is a continuous time Fourier transform of Ax1 of t plus Bx2 of t. Hence, linearity property is proved. We go on to the next property, time shifting property of continuous time Fourier transform. So the statement goes like this: if x of t is the Ctft, if x of j omega is the continuous time Fourier transform of x of t, then x of t minus t naught, if you apply Ctft, the corresponding transform will be x of j omega multiplied by e power minus j omega t naught. So you can see that the property is, if your original signal x of t Fourier transform is x of j omega, then if you perform a time shift in your original signal by t naught time units, what will happen to your Fourier transform? What will be the change in Fourier transform? The change is your original Fourier transform will be getting multiplied by e power minus j omega t naught. So this term is contributed because of this particular shift. So this is a property called as time shifting. So a time shift of t naught in time domain gives rise to multiplication of its Fourier transform by means of e power minus j omega t naught. The proof of this is simple. See, proof you have to use only two equations. One is your analysis equation, that is equation for continuous time Fourier transform. In some cases you will not be able to use Ctft. There you will be using synthesis equation, that is inverse Fourier transform. For this time shifting property, we can very well prove with the analysis equation itself. So we know very well that continuous time Fourier transform of x of t is nothing but x of j omega, which is equal to integration. So this formula we know. So now what we are going to do is, this is nothing but x of j omega is nothing but continuous time Fourier transform of x of t. So now what we want is continuous time Fourier transform of x of t minus t naught. So Ctft of x of t minus t naught will be equal to, in this equation, wherever, that is in this equation, instead of x of t you have to replace it as x of t minus t naught, right? Because if x of t Fourier transform is this, right, then x of t minus t naught Fourier transform is just this x of t signal will get replaced by x of t minus t naught. So now you have to do certain manipulations and try to arrive at this particular proof. So now what can be done? What we are doing is, we are taking, let t minus t naught is equal to a constant tau, right? So tau here is a constant. Please note down that here t naught is a constant, t is a variable, right? So a variable minus a constant will definitely be a variable. So t and tau are variables, whereas t naught is said to be a constant, right? So keeping this in mind, we can go for this integration. So integration minus infinity to infinity. So here you can see that in the place of t minus t naught, I am replacing it by tau, right? Automatically you can also see limit also, since you are replacing x variable by tau, this integration also will become tau. So what will happen to the tau limits? Since both the tau limits are minus infinity to infinity, so definitely if t is minus infinity, tau also will be minus infinity. So limits will also remain the same. So e power minus j omega, in the place of t you are replacing it as tau plus t naught into d of, in the place of t we are replacing it as d tau, tau plus t naught. So next step is, here the integration limit should be with respect to tau, because we have changed the variable of integration. So here x of tau, expand this e power minus j omega tau, e power j omega t naught, d of tau plus t naught. So next step is equal to, we are going to bring out the constant of integration over here. So what is the constant here? E power minus j omega t naught is constant, right? So we are bringing e power minus j omega t naught outside. X of tau, e power minus j omega tau, this is dt, right? D tau. Dt naught will not have an impact because t naught is going to be a constant. So a differentiation of a constant will be 0. So So simply we'll be having d tau. So this can be written as, and here the variable of integration will be tau, right? So now you can, very important inference. So now this equation can be written as x of j omega, because the only difference between this and the previous one is both are same. The only thing is there the variable of integration was t. Here the variable of integration is t, right? Here you had t, right, the limits, but here the integration is just tau. So this equation can be written as e power minus j omega t naught multiplied by x of j omega, and hence the property is proved. Ctft of x of t minus t naught is e power minus j omega t naught into x of j omega. Then we move on to frequency shifting property. So if x of t, Ctft is x of j omega, and then if the signal x of t is shifted in frequency, right? If that is, if the signal x of t is multiplied by the complex exponential signal e power j omega naught. So note down that here the constant here is omega naught. So if the signal is multiplied by e power j omega naught, correspondingly the frequency spectrum here gets, the frequency gets shifted by omega naught. That is why the name is given as frequency shifting. So now the proof for this is very simple. Again we know that, you know, continuous time Fourier transform of x of t equal to x of j omega here, right? Here we are going to exploit the concept. We see, for each and every proof we need to adopt a different methodology so that we will be arriving at this particular proof. So here we cannot go for finding Ctft of e power j omega naught xt equal to so and so. If you do like that, you won't be arriving at the proof. So what we are trying to extract over here is, from the equation you can see that here we are having x of j omega, right? Because here also we are having e power, here we are having j omega. So please note that since you are having here j omega, you will be also having here j omega. So now Ctft of e power j omega naught t x of t excuse me, integration t equal to minus infinity to infinity x of t e power minus j omega t into, because here in the place of x of t we are going to replace it as e power j omega naught t into x of t. So that is brought over here into dt. So now in this you can group the values of t. So what we are doing is t minus t naught is equal to tau. So integration see, it should not be t minus t naught. I'll just tell. This is integration x of t e power minus j omega minus omega naught into t dt. So this will not have, it has just been taken over from the previous slide, so you won't have this. So this has been just compressed into omega minus omega naught, and this is equation number 2, right? So now if you compare equation 1 and 2, it is very evident that, see, it's very evident, right? You can follow that. If I am having here j omega, I will be getting here j omega. Note down, I have to get limit t minus infinity to infinity x of t, then e power minus and dt. So here we are getting the same thing, minus infinity to infinity x of t e power minus and then dt. So what is differing here? There you had omega, here you are having omega minus omega naught. So obviously what will you get on the left hand side? In the left hand side you will be getting, instead of x of j omega, you will be getting x of j omega minus omega naught. So that will be the only so that is what we are trying to infer. So when you compare these equations 1 and 2, you can tell that Ctft of e power j omega naught t x of t is equal to x of j of omega minus omega naught. So this is called as frequency shifting, right? So next property is differentiation in time domain. So what will happen? So the property goes like this. If x of j omega is the Ctft of x of t, then j omega into x of j omega will be the Ctft of dx of t by dt. So very simple property. If a signal is getting differentiated in time domain, then In frequency domain, it will get multiplied by j omega. That's it. So applying this, for this particular property, we cannot go for the analysis equation. When you go as per the analysis equation, we will not be able to prove. Hence, we are taking the synthesis equation, that is inverse continuous Fourier time equation. So x of t equal to 1 by 2 pi integration t equal to minus infinity to infinity x of j omega e power j omega t d omega, and this is equation number 1, right? So now you can see here, this is x of j omega, this is x of t, 1 by 2 pi should be there, minus infinity to infinity should be there, here e power j omega t d omega, right? So now to prove this property, differentiate on both sides of this equation. On both sides of this equation, differentiate with respect to t, right? So that I'll be getting dx of t by dt. So dx of t by dt equal to 1 by 2 pi. Here, which is dependent upon t? You can see that only e power j omega t is dependent on t. So x of j omega d by dt e power j omega t d omega, right? So now you can differentiate this with respect to t. So when you differentiate with respect to t, you will be getting j. See here, if you differentiate, you will be getting e power j omega t multiplied by j omega. So grouping the terms together, you will be seeing that, see whatever is highlighted in red, right? So compare this equation, right? You compare this equation, one second. You can compare this equation with equation number 1. Just see what are all is given in red, right? So when you compare, it is very much evident that if x of j omega is the Fourier transform of x of t, then j omega into x of j omega will be the Fourier transform of dx of t by dt, right? So this is a proof. So we'll go on to the next property. So the next property is differentiation in frequency domain, right? And it is a continuous time Fourier transform. So the property goes like this: if x of j omega for Ctft is x of t, and then j into d by d omega x of j omega will be the Ctft of t into x of t, right? This property is also called as multiplication in time domain, because if your signal is multiplied by a time factor t in time domain, then in Fourier domain it gets multiplied by j and gets differentiated by omega. That is why this property is called as differentiation in time domain, or it is also called as multiplication in time domain. So the proof is very simple. Here we know that the Ctft of x of t, as usual we know the formula. So here to prove this, we are differentiating. See, Ctft of x of t equal to x of j omega. Note down that we need d by d omega. So we are exploiting this, right? So this we are differentiating on both sides with respect to omega. So d by d omega, here which factor is dependent on omega? The one which is dependent is e power minus j omega t divided by d omega. So when you differentiate with the d omega, you will be getting, just differentiate, you will be getting minus jt, which we are taking it as common. Remaining factors will be inside, and minus j, you can bring it to the left hand side. So what we have done here is, this minus j we have brought down here, right? So 1 by minus j will be plus j. Then this t, I am grouping it along with x of t. So t x of t e power. This is equation number 2, right? So now again you compare equation 1 and 2, right? So when you compare here equation 1 and 2, if x of j omega is the Fourier transform of x of t, then j d by d omega of x of j omega will be the Fourier transform of t into x of t. So that is a proof. So comparing both, we can write it like that, right? So hence proved. Next is time scaling and frequency scaling property of continuous time Fourier transform. So if x of t, continuous time Fourier transform is x of j omega, and then x of at, continuous time Fourier transform will be, if you, the Fourier transform of x of at will be 1 by a modulus x of 1 by modulus of a x of j omega by a. So why this property is called as time scaling and frequency scaling is, you can see that in time domain it is multiplied by A. Similarly, in frequency domain, omega is also scaled or divided by A. That is why it is called as time scaling and frequency scaling property. Again, the proof is very simple. You need to start with the original equation. So j omega and here j omega. So now we are just putting x of, instead of x of t, we are going to put it as x of at. So you have integration x of at e power minus j omega t. So we have to do some manipulation so that we get x of t, right? So what we are doing is we are replacing at by means of some other variable. So we are replacing tau by means of at and replacing the variable of integration. So when you replace the variable of integration, automatically this variable of integration will become tau, and instead of at you will be having here tau, and here instead of t, automatically t will be tau by a. So tau by a, d of tau by a, right? We know very well that tau is, t is a variable, a is a constant, so tau also will be a variable, right? So d tau by dA, so a is going to be a constant, right? So you can take that constant outside and you will be getting it as 1 by a. So the constant can be taken outside and you will be getting 1 by a x of tau e power minus j omega by a into tau d tau. So now you can write the equation Ctft equal to, here we are taking it as a modulus of a, taking into account that a can be a real number or a complex number also. So even if it's a complex number, we need to take the magnitude part. So that is why we are giving 1 by modulus of a integration tau. So the variable of integration here should be tau. So tau minus infinity to infinity x of tau e power minus j omega by a tau d tau. So this is equation number 2. So comparing equation 1 and 2, we can very well infer, just as in the previous one, that 1 by a. So you can take this 1 by mod a inside. So you will automatically see that x of at Fourier transform will be 1 by modulus of a x of j. Instead of omega, you will be getting what? Omega by a. Because if it's going to be omega, you will be having here omega. Here it is omega by a. So you will be getting x of j omega by a. So this is 1 by modulus of a, and hence it is obtained over here. Next, let us move on to a problem. So we have to see what is the advantage of using these properties. So let us take a very typical example where we will be seeing how all these some of these properties can be used. So find the Fourier transform of x of t equal to d by dt u of minus 2 minus t plus u of t minus 2 using suitable Fourier transform properties. So by applying, so first thing what you have to infer is, here what are all are given, right? So looking into the question itself, you have to see what all will be there. So you see there is an addition of two signals. So definitely linearity property will come into account. That is first point. Then you have d by dt. So when you have d by dt, it should strike to you that just refer to the previous properties. You can put a pause and refer. D by dt will refer to the differentiation in time property. So that will come into picture. And then what else? You have here t minus 2. So t minus 2 means it is time shifting property, right? So that will also come. And then over here if you see, it is minus t. So minus t means again you will have time reversal. So there is a possibility of using all these properties in this particular problem. So first, initially by applying linearity property, if x1 of t, we know linearity property, right? So if this is going to be the linearity property statement, then x of t can be written as d by dt of u of minus 2t plus u of t. So just write as per so x of j omega, right? Fourier transform of x of t will be equal to x of j omega, which is nothing but Fourier transform of this entire equation. So Fourier transform of this entire equation. So now if you apply linearity property, Fourier transform of one signal plus another signal will be Fourier transform of first signal plus Fourier transform of the second signal. So we are getting Fourier transform of d by dt of u of minus 2 minus t plus Fourier transform of d by dt of u of t minus 2, right? Is it clear? So now how can we solve till next step? So next we need to find out what is the Fourier transform of this signal, right? But this signal is not simple, right? It's not just u of t. It has u of minus 2 minus t. And here again it has u of t minus 2. So how will we solve? We have to start with first you have d by dt, right? So you need to have d by dt. So definitely you will have differentiation in time property. So when you apply differentiation in time property, the statement you know very well. If x of t Ctft is x of j omega, then dx of t by dt Ctft will be j omega into x of j omega. So x of j omega, just go to the previous one. Fourier transform of d by dt of u of minus 2 minus t will be j omega into Fourier transform of this signal, right? That is what we have written here. X of j omega will be equal to, instead of d by dt, we have replaced Fourier transform of d by dt is j omega into Fourier transform of u of minus 2 minus t. Similarly, for the next one, Fourier transform of d by dt of u of t minus 2 can be written as j omega into Fourier transform of u of t minus 2, because here this x of j omega is nothing but what? Fourier transform of the signal from which we are starting. So where you are starting this signal from? U of minus 2 minus t. So you need to find what is the Fourier transform of u of minus 2 minus t. So now first we should find out the Fourier transform of this. For that, what we know how does it come. So if you start with u of t, when you perform time shift you will be getting u of t minus 2. When you perform time reversal you will be getting u of minus t minus 2. So now how do we find the Fourier transform of this? Definitely you need to apply time shifting property for this, and for this you need to apply time reversal property. So by applying time shifting property, if x of t, you know this time shifting property. So if a signal is shifted by t naught domain times, then it will get multiplied by e power minus j omega t naught. So Fourier transform of u of t minus t is equal to e power minus 2j omega into Fourier transform of u of t. It is a very straight inference from this property, right? So this x of j omega is nothing but what? Fourier transform of u of t, the original signal. The original signal is u of t. If it gets shifted by 2, then what will happen to its spectrum? It is e power minus 2j omega multiplied by Fourier transform of the original signal u of t, right? So what we know very well that what is Fourier transform of u of t. So we would have studied Fourier transform of u of t is 1 by j omega plus pi into del of omega. So when you substitute, you will be getting u of t minus 2 is so and so, right? So you have found out Fourier transform of, you have found out now what is the Fourier transform of u of t minus 2. So this is over, right? So this is this answer. Okay, now still we are left out with Fourier transform of u of minus 2 minus t, right? So what is the relationship between this signal? When the time reversal of this signal is nothing but this signal. Here you have t, here you have minus t. So the time reversed version of this signal is this signal. So you need to apply time reversal property. So we have not discussed a time reversal property, but the property is very simple. So if x of t, Ctft is x of j omega, then x of minus t, Fourier transform will be x of minus j omega. So applying that property, we know that the Fourier transform of u of t minus 2 is this, right? So what will be the Fourier transform of u of minus t minus 2? That is just your time reversing. So that means that here wherever you have omega, it will be replaced by minus omega. So when you apply Fourier transform of u of minus t minus 2 will be e power, in the place of omega you have to substitute as minus omega. So since already minus is there, this will become plus omega. 1 by minus j omega plus pi into del of minus omega. Then now what you have done is you have found out this one. So you have found out this also finally. So now what is our final x of j omega? Just you need to add j omega into this answer plus j omega into this answer. So finally you can write x of j omega is equal to j omega into the value that you got over here plus j omega into the value that got over here. So simplify this, you will be getting like this, right? Just simplify, just multiply and simplify, and then e power minus 2j minus e power 2j can be written as minus 2j sine 2 omega. It's a trigonometric property, right? E power j theta minus e power j theta divided by 2j will be equal to sine theta. So using that property we have written, and this is the answer. So the illustration here is, you can see that we can it is just like peeling off an onion, right? You have to try to arrive at the answer by evolving properties accordingly. So looking into the question itself, first you have to determine what are all the properties that have to be applied, and you have to apply the properties carefully so that you arrive at the answer. So the practice problem that is given for today is time reversal property. So we have seen many properties proof. So you can try for time reversal property. It's a very simple proof, you can try. And next one is, you find the Fourier transform of x of t equal to u of 3t minus 6, right? So the hint here is, you can see what are all operations are being done. So one is time shifting t minus 6, and another one is scaling property. So the hint is, you can apply time scaling and time shifting property to solve this problem. Thank you, students.